All right, hello everyone. Welcome. So in this video, we are going to talk about some introductory counting rules. So let's jump right in. I'm skipping past this first page, and we are down on this section about counting rules. The first rule that we're going to talk about is this multiplication rule. And so this rule says, given a set of m elements and another set of n elements, there are m times n ways to choose an element from each. I think this is one of those cases where the formula or the definition is really more complicated than really most problems are. And so it's a little bit easier to see what this rule means with an example. And so the example that we have on this page is about the super old Pokemon game. So Pokemon Red and Pokemon Blue were two versions that you could choose back in the day. And the first decision that you make in any Pokemon game is what starter Pokemon you want to bring along on your little journey. And so in these games, your choices were Bulbasaur, Charmander, and Squirtle. And so the question here is, how many different ways can you combine a version choice with a Pokemon starter choice? And so before we get to the formula, we're just going to make a very simple tree diagram. It's a little bit overkill for this simple example, but we're going to do it anyway. And so the first branch of our tree is the version that you choose. So you could choose either Pokemon Red or Pokemon Blue. And then the second part of our tree is the starter Pokemon that you could select. So you could either select Bulbasaur, Charmander, or Squirtle. And if you select Pokemon Blue, you still have those same three choices. And so you could see from this tree diagram that you wind up with 6 different possibilities. You could do Red, Bulbasaur, Red, Charmander, all the way down to Blue, Squirtle. And so there are 6 different ways. From the formula, this is m is 2, n is 3, and so you still wind up with the 6 ways if you bypass the tree diagram and just use the formula. Okay, so that's our first counting rule. Our next counting rules, we will use this other example, also a gaming example. So if you played the old Mario Kart on the N64, which was one of my favorite games as a kid, there are 8 different characters that you could choose from. So Mario, Luigi, Peach, Toad, Yoshi, DK, Wario, and Bowser. And then at the end of a little like Grand Prix Cup or whatever, the points are tallied and the top 3 characters get to partake in a trophy ceremony. So there are 2 different scenarios that we're thinking about here. And so we're supposing that people are betting on these on this Mario Kart game. And in scenario 1, people wager which character will get gold, which will get silver, and which will get bronze. Places 4 through 8 are not relevant, so these characters don't partake in the ceremony. In scenario 2, bettors wager on which characters will just get onto the trophy podium. So which characters will be in those top 3 spots. And so moving on to the next page, for scenario 1, that was the scenario where essentially it matters, the order matters. So who gets gold, who gets silver, who gets bronze, that's part of the bet. And so that is a permutation. And so again, we could make a little tree diagram before we get to the actual formula for counting up the number of ways that characters get gold, silver, and bronze. And so you could think about this 3, 4, 5. So Mario might get gold. And if Mario gets gold, then there are 7 different options for who can take silver. But you could do this for each of the 8 characters. So Luigi might get gold, and again, there are 7 different options for who gets silver, and you could do this all the way down to Bowser, but I'm not going to draw it all the way out. Then for each of these branches, so I'm going to use a different color. So suppose Mario got gold, Toad got silver. Then for the bronze, there are now just 6 different ways once we make it through this part of the tree. And so Mario, Toad, that leaves you with Luigi, Peach, Yoshi, DK, Wario, Bowser. And that's true for every little branch on this diagram. And so what this amounts to is there are 8 different ways that that characters can get gold. There are then 7 characters left for silver for each of those branching paths, and then there are 6 characters left for bronze. And so that gives you, if you make that calculation, 336 different ways. With this permutation formula, you could also jump straight to it, though I actually find that using this type of logic that we've written out is, to me, a lot more intuitive. But you wind up with the same answer. And so this formula up here reads N is our 8 characters. R is the number of distinct objects that we're taking from those set of 8 characters. The number of distinct characters, in this case there's 3, because we only care about the top 3 characters who would be on the trophy podium. And so the formula says that that would be equal to 8 factorial over 8 minus 3 factorial, which if you simplify this, you wind up with 8 times 7 times 6 times 5 factorial over 5 factorial, and you wind up with the same exact calculation. So it's up to you what which of those methods you want to do. We'll make one final note here that this is the setting where order matters. And so in this scenario 1, Mario, Toad, Bowser is distinct from, say, Toad winning, Bowser getting second, and Mario getting third. So the order that the characters finish on that trophy podium does matter for this first setting. In scenario 2, that was the one where we only are betting on which 3 characters will be in those top 3 spots, but we don't actually care who gets gold, who gets silver, who gets bronze. We're just betting on who's going to be on the podium at all. And that's a slightly different setup. And so that is going to use this combinations formula, which we will use quite a bit. And so this is read as N choose R. And so again, N here is 8, R is 3. And so we can calculate this as 8 factorial divided by 3 factorial times 5 factorial, and you wind up with 56 ways. Notice that there are fewer ways when the order does not matter than when order did matter on the previous page. And so again, in this setting, MTB is not distinct from, say, TBM. So we no longer care about the order of those top three. Okay, one final note. So we'll get to this bottom part in class, but one final note is that in R, which we will be using from time to time for some calculations, the function that you would use to actually calculate 8 choose 3 is choose 8 3. So for now, you're welcome to use R if you want to make this calculation. You're also welcome to just use a calculator. You're welcome to use AI to make this calculation, whatever you find easiest to actually use.